Dear students, welcome back to the one more lecture on physics of nanomaterial. Last class we have discussed about what happens to the property, as we are discussing about the property of nanomaterials. What happens to the property as we decrease the size? That's called size effect. There is one more factor that influences the properties of nanomaterial, that is called quantum confinement. So today we'll discuss about what is this quantum confinement. And do you remember when we introduced this, while introducing this course, I told you about nanomaterials are very fascinating, something like quantum dots and all, when it comes to solar cells and LED applications and all. So let's see that example once again for refreshing your memory. So what are quantum dots?
Are small semiconducting nanocrystals that can be made up of a variety of different elements, such as silicon, cadmium selenide, or cadmium sulfide. They range in size from 2 to 10 nanometers. 1 nanometer is about the width of 2 silicon atoms. These semiconducting materials are able to absorb light. When they release that energy, they transform it into a different color of light. The specific color that a quantum dot will produce depends mostly on the size and material of the quantum dot. The reason for this is something called quantum confinement. The effect is similar to that of two different sized bells. When the larger one is struck, the result will be low energy sound waves. While the smaller one creates higher energy waves. When light excites a quantum dot, the larger the size of the dot, the lower the energy waves will be, resulting in a redder light. The smaller it is, the bluer the light will be. Quantum dots are currently used in biological and medical research, as well as in solar panels, televisions, and solid-state lighting.
Now you have seen the video and you understood that because of the size, there is something called quantum confinement. So what it means is, like if I say the structure, a bulk structure, the dimension is 3-dimensional and there is no confinement. So it is not bound in any directions. When you say thin film, it has 2-dimensional and one dimension is confined. An atom or the molecule or electron cannot move in one direction. Other 2 directions it's free. So that's why it's called confinement dimension is 1. So nanotubes and nanowires, it is a 1-dimensional object. Other 2 dimensions are confined. So nanoparticles or the quantum dots, they are 0-dimensional particles and they are confined in 3 dimensions. So what does this mean actually? What does this mean to us when it is say that quantum confinement? So this is what happens. The physics at different levels, so the micro or the nanostructure. So here what happens is the E space or K space, which is continuous, because of the confinement it becomes discrete. So do you remember in the first semester we spoke about in modern physics, we told about something called particle in a box, that is like discrete. So discrete, and you also remember the band theory. Why the band comes? Because of the continuous nature of the materials. So because of that you have a band structure, and here also you see that in bulk there is a continuous E space or K space, and here it is a discrete K space. So because of this and the quantization of the current, because we don't send all the currents through that, only certain currents will be certain currents only can be sent through this. So because of this, these properties are because of your confined quantum confinement. So to recall, let's see, like this is the energy level of a material, and what happens when you have only 2 atoms. So there are 2 distincts, 3 distinct degenerations, 14 if you say there are 14 degenerations, and 60, 26, 44, and when we have infinite atoms we have a continuous band. So this is how we define the band theory. Now what happens when you go to the nanomaterials or say quantum dots? You are somewhere in this region. So what you see here is atoms or the electrons are not allowed to go to any band within this. So they are only having a discrete bands. So this is what causes the quantum confinement or the quantum dot, whatever we have seen the effect. Like smaller atoms, they have a less number of atoms, and higher that they have a more number of atoms, and the energy gap reduces. So because of that, as you see in this quantum dots, the phenomena, smaller atoms, they need higher energy, that's why they emit blue radiation, and larger atoms, they need small energy, so they radiate red lights. So these things are like density of state, you will learn in your next class. So just for your information, I'm telling you, look at this. The density of states is a continuous density of state. It tells you that which all the states a material can, or which all the energies the material can take. Roughly, that's what it means. You can take that for the time being. So it is a continuous band, where when you go to two-dimensional, there is a discrete bands, and when you go to one-dimensional, you can see that there is a specific spikes. Means these are the only allowed energy levels that your material can exist. So now, because of the quantum confinement, the electrical property of the material get influenced. So the conduction band, the energy density conduction band, the spacing between two energy, then they have different electronic structure, electronic separations, and ionization. So this, because of this property, you have a whole lot of different new applications that can be thought of from the nanomaterials. So that is what you need to do in your out of class assignment. What you have to do is, as you understood little, that as you reduce the size, there is something called quantum confinement also happens. So now think about what all the electronic properties along with the applications that can be influenced because of the quantum confinement.